In this video, we will discuss the metric and the structure that endows a manifold, including a global causal structure. The metric is an additional structure on a manifold, and as we will see, it provides locally inertial frames, and that allows us to do physics in a way that it is easy to understand. It also provides the notion of causality in the case of pseudo-Riemannian manifolds. We have a notion of past, a notion of future, and a notion of a maximum speed of light. We are also being provided with a tool to measure lengths of paths in a coordinate-independent way, and in the case of pseudo-Riemannian manifolds, these lengths will correspond to the proper time that the watches of observers measure. We are also provided with a structure that allows us to define parallel transportation and geodesics. Geodesics are the generalization of straight lines in flat space and space-times, and they are the straightest, in a local sense, possible curves connecting neighboring points in a manifold. And in physics, they play an important role because these are the paths of the freely falling observables follow paths that are geodesics in the metric that we have on the manifold. Last but not least, there is a curvature associated with the chosen metric, and the curvature provides the physical degrees of freedom of gravitation. Let's start with the simple case of Euclidean geometry. We go to three-dimensional space, and there we know how to do geometry by computing lengths of paths. And if we choose to do that on infinitesimal paths, and we choose Cartesian coordinates x, y, and z, then the path of an infinitesimal line segment is given by the Pythagorean theorem by this equation here. But we already know and have a lot of experience on how to do that. We can compute the length of this infinitesimal path by using any coordinates we like, and we can express this length in terms of the chosen coordinates. So this is the example of spherical coordinates, which is quite familiar to most of you, and the case of cylindrical coordinates. But we can do that for any coordinate system that we want to pick. Therefore, in general, we see that in any coordinate system, we can express the line element of an infinitesimal path as a quadratic form of the displacements dx mu and dx nu. And you see that this expression is symmetric under the exchange of mu and nu. Therefore, the coefficients here are symmetric under the exchange of the indices mu and nu. Therefore, we are led to conjecture that these numbers here that allow us to compute lengths correspond to the components of a U02 symmetric tensor. We can use the formulas that we wrote to compute infinitesimal paths to compute the length of any curve of any shape. Well, of course, it has to be kind of smooth, but that is not really a problem. So we can split the curve into infinitesimal segments and sum the lengths over the full curve, and that means to integrate this line element ds along the path. So in Cartesian coordinates, this is done formally by computing this integral, and the actual meaning of the integral and the way to compute it is, of course, to express the coordinates as a function of the parameter that defines the curve, and this dx, dy, dz are the rate of change of the coordinates along the motion on the curve. We can do that in any coordinate system by replacing this expression here by this more general expression, and we can compute the length in any coordinate system by computing this one-dimensional integral with respect to the parameter of the curve dt, integrating this quantity, which is only a function of t. Now, in the case of R4, we usually use a different metric. We want to think of R4 as not consisting of space points, but of space-time events. So each point on this manifold consists of a place and a time that it occurs. And it is given by 4 coordinates, t, x, y, and z, when we pick the coordinate system of an inertial observer. So if we take any curve on that manifold here, it represents a curve along space-time events, and if this is a timelike curve, as we will explain later, this corresponds to paths of real massive particles or any observer. So the events P1 and P2 are occurring at some given space point at a particular time, and similarly the other event P2 at a different point of space at a different time. So if we move along the world line of an observer, the observer that follows that world line can choose coordinates with respect to which she stays at the same place, let's say at the origin of the axis. So in that case, the length, the space-time length between 2 events is computed in her coordinate system by setting dx, dy, and dz to be equal to 0. And you see that in that case, we only have dt squared remaining, and let's call this tau in her coordinate system. So you see that this time here corresponds to the space-time length of the curve that she followed to go from one event to the other, and that is a geometric quantity that does not depend on coordinates. And this value is equal to the amount of time that her clock was ticking from one event to the other. And because this is a geometric quantity and has a special way of describing world lines, we give it a special name, and we call it the proper time of that observer. So the proper time is a geometric concept. It is independent of coordinates. It happens to be, for inertial observers, to be the longest between two close enough events. Any other curve that connects those 2 events, if it is time-like, we have a longer time-like curve, and that's why we have the twin paradox in special relativity. So the free ages faster than anyone else, and by going through a very fast trip, you can go and meet your children and have the same age at the time of the meeting. If we consider events that with respect to an observer occur at the same time, then dt equal to 0. In that case, ds squared is nothing but the space distance that separates those 2 events. And you see that these are, in any coordinate system, can be written as the space components of the metric and this quadratic form with respect to the displacement. Let's make a digression before we go on and discuss some issues that have to do with notation. So we will present the abstract index notation that is used in complicated computations in general relativity. So far we have worked with the abstract tensor notation. We wanted to emphasize geometric properties of vectors, tensors, differential forms, etc. So we used a notation where each geometric object had its own symbol. So this is the example of a vector acting on a function, the gradient of a function, a U02 tensor expressed as a tensor product of coordinate bases and its components, the Levi-Civita tensor, etc., etc. The other way of discussing things is to choose a particular base and write its tensor in terms of its components. So we wrote down equations that involved the components of different tensors. Like here, for example, the tensor product of two tensors SNT has components, that is the product of the components of each tensor. Here we see the contraction of the indices of a 2-1 tensor, giving us a vector, etc., etc. But tensor expressions in general relativity become complicated. It is hard to have a convenient notation for contractions, and for that we want to use something like the component notation, but on the other hand distinguish equations that are coordinate independent from the ones that involve the geometric objects themselves. So we make the following convention. In the abstract index notation, a tensor is written with indices, but the indices do not represent its components with respect to some basis, but they represent the slots of vectors and one forms that accepts as a linear function on the product of tangent and cotangent spaces. So here is the example of a 1-2 tensor that is a linear function on 1 form and two vectors. So this tensor here as a function can be thought of as having three slots. The first slot accepting a 1 form and the other two slots accepting a vector each. So this thing here can be represented this way, and this is what is done in the abstract index notation. We write down indices here just to show the difference from the component notation. I use Latin indices for the abstract index notation only here. Each index here represents such a slot. So an upper index A here represents a slot that accepts a 1 form. And the indices B and C here are slots that accept one vector each. So if we want to write down the contraction or the image of the 1 form and the two vectors under the tensor T, we can write it this way, where now the index A here has to match the index A there, which means that omega is put in the first slot. Now the fact that B matches with the B here, it means that V is put on the second slot. And the fact that C here is matched with the C there, it means that W is put in the third slot. So this is an unambiguous way to write down whatever is here on the right hand side as we write it in the left hand side. So we can think of this expression here as being an expression using the components of the tensor and the 1 forms and the vectors if we want, but it also makes sense to think of it as a relation between the objects 1-2 tensor, 1 form, vector, vector. So to see why this convention simplifies expressions that are complicated. Let's start with the tensor product. So you know that the tensor product of two tensors, here we have a 1,1 tensor and a 0,2 tensor, is a 1,3 tensor. Therefore, it is a linear function of a 1 form and 3 vectors. So instead of writing all this, we write this. And you see this has a simple product-like looking expression, TNS, which actually means what is here on the right-hand side. And we can do that because it is consistent with the definition of the tensor product. So if we compute the contraction of the tensor product with omega, v, w, and u, by definition we know that this is the product of the contraction of t with omega and v and s with w and u. So this is how it would be represented in the abstract index notation, and you see that this is indeed equal to this one if we group the terms on the left-hand side as it is shown here. But things are even more simple when we consider contractions, and this happens very often in tensorial equations in general relativity. The simplest case is to take the trace of a 1,1 tensor, so we contract those two indices, and this is a scalar because it is obtained by taking a basis, EA, its dual basis, which is one form, so we put the same vectors and dual form here, and we sum over all the possible values of C. And that gives us the left-hand side. So you see this is a much more convenient notation because it does not refer to the choice of the basis EC. And indeed we know that if we choose any other basis, E prime, then the result would be the same. So this also manifestly shows the coordinate or base independence of the contraction. Now, if we consider more complicated cases, like here we have a 1,3 tensor, where we contract the upper index A with the middle index here. So if we write that in the tensor notation, we would have to choose a basis and its dual, put the 1 forms in the first slot, the vectors in the third slot, sum over A, and that would give us a tensor that would have 2 empty slots for vectors. So you see here, A and A are the same, therefore these slots are shown to be full. And we have 2 free indices, B and D, showing us that there are 2 free slots to put vectors there. So imagine when we have complicated contractions, how much easier to write the left-hand side compared to what if we had to write the right-hand side. Also, symmetry operations on tensor are much simpler in the abstract index notation. Here we write down the simplest cases of symmetrizing and anti-symmetrizing a 0,2 tensor. But imagine the case where we have tensors with many more indices, and then we have to symmetrize or anti-symmetrize between subsets of their indices. It's much easier to write that in abstract index notation. Now, in the following, we will use both notations because none of them solves all the problems. First of all, the abstract tensor notation gives us a deeper understanding of the geometric meaning of an equation. So, when we want to emphasize geometric properties of some equations, we may use the abstract tensor notation. Furthermore, the abstract tensor notation is more convenient when we deal with situations where we have to do algebra with differential forms. The abstract index notation in that case is many times is not found very convenient. It's also better when we have lots of things to do with Lie derivatives and Lie brackets. Well, these are, more details. Now, the abstract index notation will be used a lot in general relativity computations, and its advantage is that we still use the simplicity of the component notation, but on the other hand, we put ourselves in a state where we look at the equation with a geometric eye, and it is a very good exercise when you're not interested in just getting the result of the computation, but you want to understand what is really going on, is to look at an equation and look at the tensors involved as geometric objects instead of just having to do algebra with their components. So now let's go back to the metric and see how it is defined. So a pseudo-Riemannian metric is a choice of a U02 smooth tensor field. And I stress the word choice because on a given manifold there is an infinite number of choices among metrics that are possible to put on a manifold. As we have already said, in order to endow the metric with the power of computing lengths, we have to choose the tensor to be symmetric. So formally, that means that GUV must be equal to GVU for any vectors or vector fields in the tangent space. But it should also have another property that, at least in this class of general relativity, we will enforce, is that the metric is non-degenerate at each point of the manifold. And what this means is that if we stay in the tangent space of a manifold, the only vector whose inner product with all vectors in the tangent space is 0 is the 0 vector. And I use the word inner product because the metric defines an inner product on the manifold, which sometimes we denote it with just a dot here, and what we actually mean is the image of V and U under G. Riemannian metrics are important in geometry. In general relativity, we will not work with Riemannian, but with pseudo-Riemannian metrics, but let's mention what they are. So property 3 is getting this stronger version where we enforce that when U is squared with respect to the inner product, this is always a number that is positive or 0. And this is 0 only for the 0 vector. And there is a theorem that every manifold has a Riemannian metric. And the reason for this is because by its definition, the manifold is locally diffeomorphic to Rn, and Rn has a Euclidean metric. And if you pull back this metric locally, it is possible to do that and extend it over the whole manifold in a coordinate-independent way by using a partition of unity. You can look it up in a differential geometry book if you like, but it's not of our interest to discuss it further. But the reason I mention it here is because you should always remember that the manifold has many metrics, and those metrics can be completely different from each other as being Riemannian or pseudo-Riemannian. So when we do geometry on a manifold, we choose which metric we want to do geometry with. In nature, that means the general theory of relativity, the metric is chosen by the dynamics, and the dynamics are given by Einstein's equations. And we will see that Einstein's equation also involve the distribution of matter. So the matter is interacting with the geometry, and among the infinite choices of metric, we pick metrics that are given, that are solutions of those equations. Now, an important conclusion that we reach from property number 3 is that if we look at the matrix that is formed by the components of the metric at a particular basis, then this matrix is invertible. And that is equivalent to saying that the determinant of that matrix is nowhere zero. And this is very important because we have already seen that on a manifold with metric, we can define a volume form given by the Levi-Civita tensor, which is given by the square root of the determinant of the metric. And this property here tells us that this is a nowhere vanishing 4 form and defines a good volume element. Indeed, if we consider this equation for any vector v, it will give us a set of equations for the components of the vector u. So let's first choose for v, since we are free to choose, since this equation holds for any v, we are free to make any independent choices that we like. So let's choose for v to be the vector with components 1, 0, 0, 0, 0, and that will give this equation for the components of the vector u. Then we choose the vector 0, 1, 0, 0, 0, we obtain the second equation, and finally the vector with components 0, 0, 0, and 1 in the end. That will give us the nth equation, where n is the dimension of the manifold. But we know from linear algebra that this linear system, which is an n by n system here, and equations for n unknowns, has only trivial solutions, as the axiom says, if and only if the matrix G is invertible. So for convenience, we denote the inverse matrix here to have components having the same symbol G, but now putting the indices mu and nu upstairs instead of downstairs. So the condition of being the inverse is this one, which means if I multiply this with the matrix G, then I obtain the unit matrix. The components of the unit matrix are nothing but the components of the Kroneker's delta symbol. And we also see that this is also a symmetric matrix. We will soon see that these set of numbers that form this matrix are components of a symmetric tensor. And this is important because we wanted to be consistent with the abstract index notation. When we write G with mu nu upstairs, we want this to be a 2-0 symmetric tensor in an abstract equation. And we want, when we contract the second index with the first index here, to give us Kroneker's delta. So let's see how this happens. And the reason to find that tensor, the way to find that tensor is to construct an isomorphism between initially between the tangent space and the cotangent space using the metric, and later between tensor spaces of specific types. So let's first look at the isomorphism that the metric induces between the tangent space at the point and the cotangent space at the same point. Let V be a vector in the tangent space. Then if you consider the metric G with one slot filled by the vector V, that gives us a one form, because this is a linear map on vectors. If we call this one form by V tilde, then in abstract tensor, abstract index notation can be written this way. Then this one form is unique, and what we do for convenience is we drop the tilde and write V with the index mu downstairs. So V with index upstairs is a vector, and V with index downstairs is a one form. And these are connected via the metric G in this isomorphism between those two spaces. Now, this operation of mapping this vector to this one form is called index lowering, because when we write this equation, it looks like we take this index and we bring it down by acting with the metric G. Now, let's go the other way now and consider a one-form omega in the cotangent space. Then we define a vector omega tilde from this relation here. The left-hand side is known, and it occurs independently of the existence of the metric. It is the action of omega on any vector v on the tangent space. The right-hand side is something that depends on the metric g, and it is the inner product of omega tilde with v. And in abstract index notation, we can write this equation like this. Now, let's go to a particular coordinate system and consider this equation written for the components of those tensors. Since this equation is valid for any v here, then omega mu will be given g nu mu times omega nu tilde. Sorry, I rushed a little bit. We don't need to consider these equations as being components, since this gives the action of omega on any vector v, and this tensor here, this one form on v, then those two one forms must be equal. And of course, it is also valid if we consider components in a particular basis. But now we will consider this equation as equation between components and act with the inverse of the matrix G. So we multiply the left-hand side by g mu lambda, and we do the same thing with the right-hand side. But then you see that this product here will just give us delta lambda nu, because g here is the inverse of g there, and that will give us omega lambda, omega tilde lambda. So omega tilde lambda has components that are obtained from the components of the one form omega by multiplying with the component, the g lambda mu numbers here of the inverse of g, and summing over the indices mu. Of course, soon we will see that this is a 2-0 tensor, so this will also turn out to be a tensorial equation. Again, for convenience, we drop the tilde because there's no confusion. We put the index up, and that is different from having the index down. So omega mu index down is different from omega mu index up, one form vector. So we don't need the tilde to carry it around and confuse us. So this operation here is called index raising, because by acting with g on omega, it looks like we take the index mu and we put it upstairs. And by doing similar contractions with tensor of any type, we can perform the operation of raising and lowering indices in any tensor we like. So this is an example, and we have a 2-0 tensor where we lower the first index. So we act with g mu lambda, sum over lambda here, and we obtain a 1-1 tensor. We can go ahead and repeat this operation and lower also this index here and obtain a 0-2 tensor by acting with again with the metric. And you see that we can lower both indices here from the beginning by acting with the metric in this particular fashion and do the appropriate contractions. Now let's define the tensor g tilde with indices upstairs to be a tensor having those components. So what we actually do is we take the metric and use the inverse metric here to raise the components rho lambda and put them upstairs. So you see here that we have two different objects. On the right hand side we have the inverse of a matrix, and the left hand side now we have a tensor. So you see that the inverse of the matrix and this tensor here are one and the same, and that is why we drop the tilde and we use G with indices upstairs both as the inverse of the matrix G mu nu or as the tensor with raised indices by the metric. Indeed, this tensor here, when it acts on G, and we contract those indices here, U and U, then by applying the definition that we just made by index raising, you see now this is the inverse matrix, will give us a delta, then that will give us another delta there, and the two deltas here will give us the unit matrix, the components of the unit matrix. So the components of G tilde are acting the same way than the inverse of the metric does. So the components of those objects coincide in any base, therefore they are the same. Finally, notice that if we lower the index of the vector and we obtain this one form, v tilde, then we can raise it back by using the inverse metric. Now that will give us a different vector, but as you can see, because this is the inverse of the metric, v and v double tilde are the same vectors. And that is why this operation of index raising and lowering is a one-to-one onto matrix mapping and creates an isomorphism between tensor spaces of type Lk for L plus k fixed, which means that they have the same number of indices. It is very important to realize that this isomorphism exists and depends on the choice of the metric. So if we have not picked a metric, then we have not chosen such an isomorphism, and we cannot raise and lower indices. It also tells us that it depends on the metric. So if we map this vector here to this form, then if we choose a different metric, then the same vector will be mapped to a different one form. So if we don't have a preferred metric, then we don't have such a preferred mapping between vectors and one forms, and this can be generalized to any type of tensor. Now let's look at the component transformation of the metric in a little more detail. If we first choose a coordinate basis and then transform it to a different coordinate basis with coordinate transformation, we know that as for any tensor, the components of G will be transformed according to this law here. Now, if we define the matrix lambda here to be the Jacobian, having as elements the derivatives of x with respect to x prime, we can write this equation as a matrix equation that involves the components of G here and lambda and the transpose of lambda. And we can do that for any change of basis, whether it is a coordinate basis or not. So if we have any basis E, we can transform that to any other basis E prime by using a non-degenerate matrix lambda, which gives the vectors of the basis E prime as a linear combination of the vectors in the basis E. Then the inner product of two such vectors in the new basis will give us the components in the new basis of the metric, and by substituting this linear expression and using the linear properties of the mapping G, we arrive at the same expression like we have here in the case of transforming between coordinate bases. So this equation here holds for any basis transformation in the tangent space. So if we look at the components as a symmetric matrix, we know from linear algebra that it has real eigenvalues. And because we have postulated that this matrix here is invertible, then all those eigenvalues must be different from 0, because the determinant is the product of the eigenvalues, and if any of them is 0, then the determinant is 0. Furthermore, there is a theorem in linear algebra saying that there exists an orthogonal matrix, which means that its inverse is equal to its transpose, such that if we make this similarity transformation of the matrix G, we obtain a matrix in diagonal form. So this matrix here is not any matrix, it gives us the eigenvalues of the metric, and the columns of this orthogonal matrix contains the eigenvectors of the metric. Then we will use another theorem from linear algebra that says that any such matrix here, which is non-degenerate, can be written as the product of such an orthogonal matrix and a diagonal matrix. And of course, if we take the transpose of this equation, we can compute the transpose of lambda to be given as the product of the transpose of D and the transpose of O. But the transpose of a diagonal matrix is itself, and since O is orthogonal, then the transpose of O is just its inverse. So if we substitute this for this, so that means we make this special coordinate transformation, then we find here that the diagonal matrix containing the eigenvalues of the metric here is multiplied from the left and the right by a diagonal matrix, and let's say that the non-zero elements of that matrix here are the diagonal elements d0 through dn minus 1. And of course all of them have to be non-zero if we want the metric to be non-degenerate. So this multiplication is very easy. It just gives us back a diagonal matrix with elements g0 through gn minus 1 multiplied by the square of the diagonal of the matrix D. So let's do now the following. We will apply this formula in the following procedure. Now, take the metric and its components in any base that you choose. Diagonalize it and compute the orthogonal matrix O. Then choose a basis that is related to the original one that you started from with a transformation lambda that is equal to this O times D, where D is chosen to be the diagonal matrix, which is 1 over the square root of the absolute value of the eigenvalues of the metric. In that case, in this new basis, the metric will have components that is given by this product. And you see this is the same formula as this one, but instead of D, we have the chosen values 1 over square root of G. So you see that this will give us a diagonal matrix with the components in this new basis, E prime, which all of them are equal to the eigenvalues of the metric divided by the absolute value of the eigenvalues. And of course, this is just the sign of its eigenvalue, which can be either plus or minus 1. So we have chosen a basis where the metric is put in a diagonal form containing non-zero elements that are on the diagonal, of course, and take values either plus or minus 1. Now, by changing the order of the eigenvectors in the columns of O, we can bring all the negative eigenvalues in front. Therefore, in this transformation, we can have all the minus 1s in front and all the plus signs behind. Of course, that's a choice. We could have done it the other way. It doesn't matter. This is called the canonical form of the metric, and it is always possible to put a metric in this form. But the number of minus 1s that we will find after we're doing this cannot be changed with the basis transformation. So this is a property of the metric, and it is called the signature of the metric. When we put the metric in this canonical form, that means that we have chosen a basis where its vectors are orthonormal. That means they're orthogonal to each other, and when we compute the inner product with themselves, we get either a plus or minus 1. Now, for convenience, we call this sequence of minus and plus 1s with the symbol eta mu nu. And we are quite familiar with this in the case of Minkowski space, where the signature is equal to 1. We have only one minus sign, and all the others being pluses. But this base is not unique. There are many bases that, when you transform from, let's say, the basis E prime to the basis E, using matrix lambda, that still the new basis is again orthonormal in the same way, in a canonical form. And this is done whenever this transformation matrix obeys this equation. That means that if you multiply lambda by eta and then by the transpose of lambda, you get back eta. Indeed, you see that if you take the inner product of the vectors in the new basis, this is just a linear combination that defines a transformation. Here we use the linear property of the tensorial map, and we end up with this matrix here, lambda transpose eta lambda. But we have assumed that this is a transformation where lambda satisfies this equation. So lambda transpose eta lambda gives us eta. So this basis here has inner product that is the same as the inner product between the vectors in the previous base. So both those bases is orthonormal. And we know from group theory that this equation has many solutions, and the solutions form groups. So for example, when we have a positive definite metric, a Euclidean metric where its signature is 0, there are no minus signs in its canonical form, then the solution of this equation forms the orthogonal group. And you can see that when S is equal to 0, eta is nothing but the unit matrix. So this condition becomes just that lambda transpose lambda is equal to the unit matrix. So this is the definition of the orthogonal group. Now, in the more interesting case for us, where the signature is 1, we have 1 minus sign and all the other pluses, the metric is called Minkowskian. And the lambdas that satisfy this condition form a group that is called the Lorentz group, that you are familiar from the special theory of relativity. But we must stress that orthonormal bases are possible to construct, but they are not coordinate bases. That means they are not globally defined coordinates on a manifold whose coordinate vectors are everywhere orthonormal, unless M is a flat manifold. Coordinate bases, of course, can be for some metrics orthogonal to each other, but you cannot make all of them to have unit length in a neighborhood of a point. We know such an example in the case of the Euclidean space. If you choose spherical coordinates, r, theta, and phi can be the unit vectors in the r, theta, and phi direction. You know these are defined to be orthonormal, but the coordinate vectors dr, d theta, and d phi are not orthonormal. They are orthogonal to each other, yes, but dr has a unit norm, but d theta and d phi do not have unit norms. The norm of theta is increasing with r, and similarly for given theta, the same thing happens for d phi. But life is not as hard as we think. We can always choose a coordinate system such that at one point the components are such that the coordinate basis is an orthonormal basis. That means that the components of the metric tensor in this coordinate is nothing but eta mu nu. And well, this is kind of trivial, but this is there's even a more stronger condition than putting the metric in this form. In those coordinates, the deviation of the metric from the flat metric is as slow as possible. And this is quantitatively expressed by the fact that the derivatives of g with respect to the coordinates are 0, the first derivatives. But if the manifold is not flat, we cannot go any further. The second derivatives of the metric components cannot be set equal to 0 even if we try. And for a simple proof of this, look at in Carroll's book in paragraph 2.5. So the coordinate basis at P is orthonormal, and this is what defines locally inertial observers or coordinates, or as we say sometimes, a local Lorentz frame. And this is a frame where physics becomes simple. So this theorem here tells you that if you go ahead and construct a laboratory that is small enough, then you can do physics that are the same as the physics that you have done in the context of the special theory of relativity. Of course, if you consider distances that are going far away, you will find deviations from the special theory of relativity, but if you do that in a small enough laboratory, then you will be fine. Now, small enough needs a scale to be defined, and that scale is nothing but the radius of the curvature. So if you live in a region where you have very strong gravitational fields, the curvature will be large, and your laboratory should be tiny in order to do special theory of relativity. But if you live in a region, like let's say on the surface of the Earth, where the gravitational field is weak and the radius of the curvature is large, you can have much larger laboratories and do special relativity physics without worrying too much. So that teaches a lesson and tells us that physics is simple locally. Unfortunately, it's not so much globally. And as we will go more into learning general theory of relativity, we will get a feeling of that. But for the moment, we are happy with the fact that we can do physics that we know if we stay in small enough locations. And as we know from the special theory of relativity, a Minkowski metric endows us with a causal structure. And that comes from the light cone in the tangent space, where you can have vectors that are timelike, light-like, or space-like. And this gives us the usual causal structure that we find in special relativity. But this causal structure can be defined on any point of space of the manifold. So every point in the manifold has its own tangent space, and it's in a small region around it. We can use the light cone to define a causal structure in its neighborhood. But this is true also globally in the manifold. So, tangent spaces move in a non-trivial way from point to point, and we don't know yet how to compare between such tangent spaces. So we can see why a non-trivial causal structure may arise when the metric and or the topology of a manifold is complicated. So what we do in GR, we say that massive particles must move on world lines where at every point on that curve, the tangent vector is timelike. And that is what defines a timelike curve. Massless particles, however, must have world lines where the tangent vector is everywhere null or light-like. And that defines null curves. So light, in a loose sense, in the vacuum, moves on such null curves. Photons move on null curves. So we will never consider for this reason curves where the tangent vectors become from time-like to space-like or from time-like to null. Curves that are physical must stay either time-like or space-like or null at every point. Orthonormal bases define what we loosely call an observer or a laboratory. So you see this nice cartoon here that you can find in Hartle's book, where you have a small enough laboratory, small compared to, as we have said, to the radius of curvature, where you can set a lab defined by a Cartesian system of coordinates given by the three normal spatial vectors, and a clock here that ticks according to the timelike vector in the base. Now, the E0 vector of that base is the forward velocity of the observer. We know that the forward velocity of the observer has a norm u squared that is equal to -1, and so is true for E0 here. So this is the forward velocity of the observer, and E1, E2, and E3 define the local Cartesian axis. In that lab, you can define and measure vectors that are either time-like, null, or space-like, according to whether they are in the light cone of that observer. Now, to see why physics becomes simple in these local frames, let's consider a particle that passes by this lab. So one quantity that could be useful for the physicist sitting here is to compute the relative velocity of that particle compared to the lab. And as we will see, such a notion does not exist globally on a manifold, but it can be defined locally because we can do special relativity physics. So because of that, if V is the forward vector, which gives the forward velocity of the particle, let's for simplicity consider it not like it is shown in the cartoon, but having the particle moving in the x direction here, like this. It has components that are given by the factor gamma that we are familiar from special relativity, 1 over square root 1 minus v squared. And the zero component is gamma, and v1 component is gamma times v, the speed. Now, in the chosen frame, the forward velocity of the observer has components which are 1, 0, 0, 0 by definition. We said u is equal to e0, therefore the component here is equal to 1. And the inner product of u and v in this basis is just minus gamma plus gamma v times 0 equal to minus gamma. So the velocity of the particle, which is 1 minus 1 over gamma square root, can be expressed in terms of a quantity that is coordinate independent, which is the inner product of u and v. So every observer can compute this inner product. It does not have to be in this lab to compute it. It can use any coordinate she or he likes and compute this number. And by computing this number in their coordinates, they can deduce what is the relative speed of the particle with respect to such an observer. If you don't like the word speed, let's consider the energy of a particle. So the energy is computed from the 4 momentum of the particle, whose zero component is the energy, and the space components is the spatial momentum of the particle. Now, if you compute the inner product of u and p, you will just find minus e. So e is given by minus the inner product of the 4 momentum of the particle and the 4 velocity of the observer. And that can be computed in any coordinate system. And the result will be the energy as measured by the observer that sits in this lab. A special class of local frames are local inertial frames. And this is a very important class because in general relativity these are the freely falling frames, which are frames that are not subject to any interaction with the four known forces in the universe. So these will be observers that will observe free particles to move while passing through their small lab on straight lines. You know that if you are an accelerated observer, for example, and you observe a free particle, you won't see it moving on a straight line. But an inertial observer should observe free particle to move on a straight line. So let's see how you can become one of those. Let's consider a particle that is free. You have determined that it doesn't interact with anything, and then what you should do is to ride along it. Of course, this is a thought experiment, and you have to figure a way not to interact with the particle while you ride along it, but this is another story. So what you will do is, by traveling with this particle, of course it's a massive particle and travels slower than the light, you set the origin of your axis to be that particle. Then, in order to define space axes that are Cartesian-like, you take 3 gyroscopes, you make them spin as fast as you can, and you make them define the x, y, and z coordinates at all times. So you have your watch or your mobile phone those days, and read the time and measure positions of particles in your lab with respect to those 3 axes, and you can record events. Now, as you move around, as you travel with a particle, these gyroscopes can be shown to stay in the quote-quote same directions. That means that they're not rotated. They're not subject to rotation. So this is why we chose the gyroscopes to give us a special class of Cartesian axes. So if you do that, then the gyros spin freely and define a spatial axis at each instant of time, and you can also show that in this coordinate system, that of course changes at each instant as you move along the curve, has the properties of a freely falling frame. That means that the metric is, of course, obviously and by construction, the Minkowski metric, but also it is as flat as possible. The derivatives of g at a particular instant of time are found to be equal to 0. So this way you can construct a lab that is small enough so that you can do your special relativity physics. Now we have to make sure that we understand that not all observers are inertial, and that is starting with ourselves. So us sitting on the surface of the Earth are not inertial observers, and the reason is because we interact with the electromagnetic interaction mainly with atoms and molecules of our chair or the floor, so we are not allowed to fall freely towards the center of the Earth. So we are accelerated observers, but we are not the only ones. We can have an accelerated lab in a rocket that burns fuel, and that is also an accelerated lab, and if this acceleration is equal to 1g, you can live here the same way we live on the surface of the Earth. other classes of inertial observers that are not inertial are rotating inertial observers. And you will ask me, rotating with respect to what? Well, with respect to such coordinate systems constructed by gyroscopes. Now, let's also look at the dual basis of an orthonormal basis. We will see that there is a sense that it is also orthonormal with an inner product defined now by the inverse metric, not the metric itself. So, any basis in the tangent space has its dual, and this is a unique basis that satisfies this condition. This is a condition that is independent of the choice of the metric. But if this metric, if this basis is orthonormal, we will show that E mu and E nu are also orthonormal. And we will show also another useful relation, which is the following. The fact that E mu and E nu are orthonormal, it means that E mu dot E nu gives eta mu nu, which written in abstract index notation or in component form, whichever you like, it means that G alpha beta, E mu alpha, E nu beta gives eta mu nu. Now, this relation can in a sense be inverted. And here you see that we put the dual basis, E mu and E nu, where mu and nu are upstairs, and their components, alpha and beta, are downstairs. Now, we sum over contractions of eta with mu and nu, not with G. And alpha and beta are now free indices, and that will turn out to be equal to G alpha beta. But that we have to see why it's true. So, let's start from the definition of the dual basis. In component form or in abstract index form, it is this equation here. But we can view it as a matrix equation relating their components in some basis that we choose. Now, if we do that, this is like a matrix equation of E tilde transpose equal to 1, where E is the matrix constructed with the alpha component of the nu vector. Nu goes to the row of the matrix, alpha goes to the column, and then the matrix E tilde transposed is constructed by the numbers which are E transpose alpha mu, alpha in the row, mu in the column, where this symbol here just is equal to the alpha component of the mu basis. So you see here it is kind of complicated, but you will see why. Now, the fact that we have written this definition as a matrix equation allows us to see that this matrix E here is the inverse of E tilde transpose. And we know from linear algebra that if we do the matrix multiplication from the other side, it should also give us the unit matrix. So if we now write the matrix elements of those matrices and multiply them from the other side, we multiply E by ET from the left, then we should still obtain the unit matrix, which is delta alpha beta. But by definition, this symbol here is nothing but the alpha component of the new dual basis one form. So we have this relation here. So we have shown that this relation should also hold between the dual bases. Here we sum over the components and get delta mu nu. That is straightforward from the definition, but we have seen that this implies that if we sum over all the elements of the basis for the components alpha and beta fixed, we also obtain delta alpha beta. So now let's compute the inner product of the dual one forms in mu and in u using the inverse G defining the inner product. So this is nothing but G alpha beta, E mu alpha, E mu beta. Now we put G in the middle here. So this is almost like a matrix equation, because you see we multiply alpha here with alpha there. So that is the column, that is the row. So what we do, so that we make this like a matrix multiplication, we have to substitute this symbol here, just to make it a matrix that multiplies, and that is multiplied by the inverse of G. So you see that this inner product is just the mu nu element of the matrix E times G minus 1 times E tilde transposed. But we have seen that the inverse of E is ET minus 1, that is E minus 1, and you know from linear algebra that the product of the inverses is the inverse of the product, but in the reverse order. So that is E times G times E tilde T. So this, by definition, gives us, because this is an orthonormal basis, right, will give us eta mu nu. And now this is the inverse of eta mu nu, but you know that the inverse of eta mu nu is eta mu nu itself. Therefore, we have that if we take the inner product of E mu and E nu, that gives us eta mu nu, implies that after multiplying by A mu gamma, E nu delta, and do this small calculation on the right hand side, you see that this is contracted with this one, giving us delta alpha gamma. This is contracted with that one, gives us a delta beta delta, and that makes the indices alpha becoming gamma and beta becoming delta. So that will give us G gamma delta. So let's look at another useful formula that will prove to be convenient later. It is not a very hard one, but let us mention it in passing. Let's consider a coordinate system that has coordinate bases that are orthogonal to each other. Not orthonormal, but orthogonal. That means that in that coordinate system, the metric can be put in its diagonal form. These are the diagonal elements of the metric here in those coordinates. And of course, in this case, the norms of the coordinate vectors are given by the components here of the metric. Now, if we define new vectors that are normalized with the square root of the corresponding components, that will give us an orthonormal basis. And you see that by definition, the components of those orthonormal vectors are nothing but 1 over the square root of the diagonal elements of the metric. So, given a metric in a diagonal form, we can define an orthonormal basis that in those coordinates has components given by those simple expressions. So let's look a little bit more now into the process of computing lengths on curves. Let's consider a metric g given by this expression in a coordinate system, and a curve where delta v here is a infinitesimal vector in the tangent direction with components delta x mu in this coordinate in this chosen basis. Then the norm of this vector is computed this way here, and you can see that after using the linear property of the tensorial map and the fact that d mu and d nu when contracted with g give the components of g, that is equal to g mu nu delta x mu delta x nu. So when this vector is contracted with the metric, it gives us the line element on the curve. We sometimes, as physicists, we sometimes write sloppily ds square equal g mu nu dx mu dx nu, meaning exactly this infinitesimal length as we move along the curve, and use that to understand the definition of the length of a curve by integrating this infinitesimal length and obtain this formula. In order to compute this integral, you have to compute the rate of change of the coordinate functions along the curve and compute this one-dimensional integral of this function of t, the parameter on the curve. Now let me also stress that sometimes in the bibliography you will see this notation ds square is g mu nu dx mu dx nu, but the author actually means this tensor. Now when this is done, you have to be careful because you cannot commute dx mu dx nu, because this is not possible when we have a tensor product. But it should be easy to understand from the context when you browse through the bibliography what notation its author uses. It sometimes can be confusing, but the more experience you gain, the more you will be able to understand and use the conventions of different authors. So, as with the case of the metric, you see that the line element can be either positive, negative, or 0 for a metric with signature 1. So curves whose line element is negative everywhere define timelike curves. You can see an example here for this curve here, and at each point of that curve the tangent vector is timelike, which means that the light cone of the tangent space, no matter how it tilts, has the tangent vector enclosed in it. So at every point this vector has been in the timelike direction of the local tangent space. In a similar way, if we have a null curve followed by a massless particle, then this tangent vector will be all the time in the direction of that falls on the light cone of its tangent space. And if we have a space-like curve, then the tangent will be always outside the light cone. But we consider curves that the tangent vector is always of the same type at each point, which means that its norm, g, v, v, has always the same sign on the curve. As we have already mentioned, timelike curves are world lines of observers and massive particles. null curves are world lines of massless particles, like for example photons. And whenever we have such world lines, either timelike or null, the tangent vector on that curve is what is called the forward velocity of the particle, massive or massless respectively. And this class of curves, timelike or null, are called causal curves because each event on the curve can influence an event that follows at a larger value of the parameter of the curve. In the special case where we have a timelike curve, we may have an observer who can choose an orthonormal frame at each point of the curve, picking E0 to be her or his forward velocity, and she or he stays at a fixed position, let's say at the origin of the action of the axis, where dx1, dx2, and dx3 are equal to 0. For such observers, the line element is nothing but the proper time that their clocks record between events that happen at the origin of the axis. So the light cone also defines the notion of what is slower moving than light, or moving with the speed of light. This is a local concept. We cannot have a relative speed for particles that are far from each other, but when they are in the same lab, in the same small region around an observer, we can have relative speeds that can be compared to the local light cone, and from that deduce whether they are massive or massless, whether they move with the speed of light or slower than the speed of light. So let's pause a little bit and look at some specific examples. Let's look at an example that you can find in the book of Hartle. That's example 7.3. And let's consider the metric which in x and t coordinates has this form: minus x squared dt squared plus dx squared for positive x. So these are not Cartesian coordinates for a flat metric. Let's see what they are. First of all, note that the two coordinate vectors are everywhere time-like or everywhere space-like. dt has a norm that is equal to minus x squared. It's always negative, so it's everywhere time-like, whereas dx has a norm which is equal to 1, which is positive everywhere, so dx is everywhere space-like. Let's consider a curve connecting two events A and B, which are happening for the same value of the parameter t. So this is a straight line in this coordinate plane. Now if you want to compute the length of that curve, the space-time length of that curve, you start by noting that dt is 0, therefore ds squared is equal to dx squared, and you can easily integrate this from position xa to position xb and find that the length of that curve is equal to the difference of the x coordinates of those two events. Now, if you consider a curve that is a line segment in this coordinate system for fixed x, then dx is equal to 0 and ds squared is nothing but minus the proper time along that curve. and that is equal to x alpha squared dt squared. So the total proper time that the clock will show moving from the event A to the event B will be the integral shown here, and it is easy to compute because x is constant, so this is x times tb minus ta. Now let's consider a slightly more complicated curve, still a line segment defined by x which is proportional to time. Well, we can add a constant here which we don't show. So d squared is minus v squared dt minus v squared t squared dt squared plus v squared dt squared. And because dx is equal to v times dt, if we substitute here, we obtain v squared dt squared, and we see that the line element along this line segment is given by this expression. So you see that whether this is time-like or space-like depends on the value of t, and it is time-like only when t is greater than 1. Now if we assume that we start at 1 and then go at later times, then we can write down the elapsed proper time to be given by this expression that involves the square root of t squared minus 1. So the total proper time for an observer moving from A to B along this line is given by this expression here. It can be integrated, and you see that we obtain this result, which is quite different than we would have obtained if we had a regular Minkowski metric where x squared would have been absent from in front of dt squared. So such a curve in Minkowski space would just give us the well-known formula that the proper time is delta t divided by gamma. So here you see we obtain something completely different. Null curves are important to be studied for this metric because this will define the causal structure and the light cones. So if we want to compute those null curves, we have to see which ones satisfy the condition d squared is equal to 0. Now for those curves, we have minus x squared dt squared plus dx squared to give 0. And we can write down a simple differential equation of t as a function of x. dt by dx is equal plus or minus 1 over x, and this can be trivially solved and give t as a function of x. So that defines a curve with parameter x, and you can see different curves here by choosing a different sign here, plus or minus, and a different x0. So you can see now why our little line segment here is not changes from space-like to time-like. Now look here, if we start from event A, then this is outside the light cone, and it is space-like here. But as we move on here, then when we reach the point B, then this direction is at least approximately within the light cone of this point here. So at this point, this curve has become time-like. So let's now show an example of a curve that is everywhere time-like. Let's consider the curve as a function of t to be given by a cos ht. So this is a time-like curve. dx dt is a sin ht, which is smaller than a cos ht, but this is equal to x. So dt by dx is larger than 1 over x, and you see that this is what defines the light cone, so this curve is inside the light cone because the derivative is larger than 1 over x. And we can easily confirm that by computing ds squared along this curve. dx is a sin ht dt, and when substituted into the form of the metric, you see that sin h squared minus cosine h squared gives minus 1, and ds squared is nothing but minus a squared dt squared. And you see that this is trivially always negative. And we also see that the proper time along this curve is proportional to dt. Let's now see another less trivial example. Let's consider a metric that describes a wormhole. That is a very nice example that you can find in the book of Hartl, example 7.7. So let's consider the metric given in terms of coordinates t, r, theta, and phi, like we do, a similar thing using spherical coordinates in flat space. And indeed, if this parameter b is chosen to be 0, then we have nothing but Minkowski metric, where the space part is in spherical coordinates. But here we will consider the case where b is strictly positive. And that, as you will see, will give us a non-trivial spacetime. Let's start by considering space at t equals constant. Now, such a space has a metric given by this expression after we set dt equal to 0, since we stay at a particular time slice of that spacetime. So this is the metric here. It deviates from the flat metric because of the non-zero parameter b that you can see here. And let's take a closer look by considering only the equatorial plane. We take theta equals pi over 2, d theta equal to 0, and then we obtain a metric d sigma square given by this metric restricted on that plane. So sin theta is equal to 1 because theta equals pi over 2, and d theta is equal to 0. So we're only left with this expression here. So what we will try to do now is to find this metric induced on a two-dimensional surface embedded in three-dimensional flat space. And that will give us an insight and a visual of how a surface with such a metric looks like, and obtain an intuitive picture of how it looks like. But it will also allow us to do more than that. So in order to do the embedding, consider three-dimensional Euclidean space and cylindrical coordinates in it. So this is the flat metric in 3D in R3, but in cylindrical coordinates, rho, phi, and z. So that is d rho square plus rho square d phi square plus dz square. That's a flat metric. And now let's consider a surface that is defined as a function of z and phi. Rho is given as a function of z and phi, so that's a surface of revolution, as you will see, given by a function that, it does not depend on phi. So we will show that such a surface will have an induced metric that is the same as d sigma square if we choose the coordinates on that surface to be r related to rho square by this relation, and z related to r with this relation, and phi being trivially the same as that in the cylindrical coordinates of R3. So if we compute dz and d rho according to the embedding equations shown here, we'll find dz to be given this function of r times dr, and d rho to be this function times dr. There's no d phi because there's no phi dependence. So if we substitute dz and d rho in d sigma square, we will find that these derivatives arise here, computed here, and rho is substituted by r squared plus b squared. So this will give us this metric here, because as you will see, their squares here add up to 1, and rho is substituted by r squared plus b squared. On that surface, it's also easy to see that when we take the points defined by r is equal to 0, they don't correspond to some specific point, like the origin in spherical coordinates, but they correspond to a circle on this equatorial point that has radius is equal to b, or in the full metric it corresponds to a sphere of radius b. Remember here that in order to get to this simple form of the metric, we chose the equatorial plane theta equals pi over 2. So the full metric here on for different values of theta will give us a full sphere instead of a circle. So what we have done is we have related r to z with this equation, and since r originally took values from 0 to plus infinity, that means starting from this circle to a place further away, we had also the coordinate z to be positive. So if we had looked at the graphic representation of this function, we would have obtained this part of this curve. But you see there is nothing wrong to extend this to negative z and obtain the symmetric part also from with respect to the rho axis. In order to do that and still have the same embedding equation, you have to consider r taking also negative values, something that made no sense when we had b equals 0, the b equals 0 case, because we were just reaching the origin of a flat space. Now we can do it because we reach this sphere and we can extend to negative z in a smooth way. So if we see this surface that is obtained by revolving this around the z-axis, we obtain a spatial geometry that looks like this one. Of course, remember that we're still on the equatorial plane theta equal pi over 2, so each circle here is actually a sphere. Notice that when we go to large rho, or equivalently to large r, we obtain asymptotically a flat space, because when r is much larger than b, then r squared and plus b squared is approximately equal to r squared. So that will give us a flat metric. But this happens not only for positive r, but also for negative r. So you have two asymptotically flat spaces corresponding to going to R to plus infinity and R to minus infinity. Now, these asymptotically flat spaces are only connected if you go through the throat of that wormhole. You have to necessarily come from here, go through the throat, and then visit the other asymptotically flat space. So this is why such a geometry is called the wormhole geometry. And the throat of this wormhole is R equals 0, which does not correspond to a point, but it is a sphere. The other non-trivial thing that we have done with extending space-time as much as we could is that we changed the topology. Notice that the topology of space is not anymore equivalent or homeomorphic to R3, but is more complicated than that. Another interesting example is the free Robertson-Walker metric written here that we encounter when we study flat space cosmology. So when we stay at fixed parameter t, dt is equal to 0, and the line element gives us the metric of flat space. And the reason why it is flat is because we have assumed that this parameter, this factor here, is a function only of t. So at fixed t, this is a constant. So that is flat space. Now, if we choose to stay at the quote-quote same point of space, that means at points for fixed x, y, and z coordinates, we are defining a so-called co-moving frame or co-moving observers. So for those observers, the line element written in these coordinates correspond to their proper time. So in this cosmology, Earth is assumed to be approximately on such a co-moving frame, and our proper time is this coordinate t that we have used to write the metric in this form. So don't confuse this with the definition of a global time, but for each co-moving frame, this parameter t gives the proper time of those observers, like us. Now, the factor a defines the scale of this flat space at a given time. And since this varies with time, then the scale comparing space at different times changes with time. And what is actually found is that this scale increases with time. So actually this factor here determines the expansion of space or the expansion of the universe. To see this, consider this picture in the coordinate plane x and t, and consider two co-moving observers. So they have fixed x, and consider two values of the time t1 and t2. So if we have a curve at fixed t1, its length will be delta S1 given by alpha, the value of A at time t1, call it A1, times delta x, and at time t2, the length of that curve will be A2 times the same delta x. Because we are co-moving observers, the coordinates don't change. So you see that although those two curves seem to have the same length in this coordinate plane, they don't have the same length defined by the metric. And the rate of change of their length is proportional to this factor A. So this is why A is called the scale factor. typically what is found is that this scale increases with time as t raised to a power that is less than 1 and positive. Examples of such values are given by, in the case where the universe is matter dominated, like it is the era that we live today, and Q takes the value 2/3. Now, in early phases of the universe, not too close to the Big Bang, of course, but less than 10,000 years, the universe is radiation dominated, and this exponent here is equal to 1/2. In all cases, however, we see that as t goes to 0, the scale factor has a limit that is equal to 0. And that points to the fact that at t equals 0, there exists a true singularity of that metric. We cannot see that yet. We don't have the tools to see that yet, but we will see that later. So, since we have a singularity at t equal to 0, space-time ends at a finite time in the past for any observer. In fact, in our coordinate system on Earth, space-time ends approximately 13.7 billion years in the past. Now, if we want to compute light rays, we have to solve the equation ds squared is equal to 0. Now, that means that light rays must be such that this equation is satisfied. Of course, we have taken the light rays to be in the x direction, putting the dy and dz to be equal to 0. And if we assume this form for the expansion and substitute it here, we have a very simple differential equation to solve, and the solution gives t as a function of x. That means a curve in the coordinate on the coordinate plane, which relates t to a power of x. Let's call it r, and r is equal to 3 in the radiation dominated era and 2 in the matter dominated era. So this is a cartoon of those solutions in both cases. So let's consider two events for in co-moving frames, and P1 and P2 happen at the same value of the coordinate time, and we see that the light cones going back to the beginning of the universe define regions of space that are finite. So as we go close to the singularity, the light cones become tangent to the x direction here, but we still see that there are points left outside the light cone of P1, which means that there are horizons defined. Let's say at this point here, that is an horizon, and every point, every event outside this horizon is not in causal contact with P1. And that is very important because we have to look at the universe, find that it is extremely uniform, and we are wondering how can points that are not causally connected have created regions, huge regions in the universe that are more or less the same. So that is an interesting problem to solve. And one way to solve it is to use the hypothesis of inflation. So this was an example of a non-trivial global causal structure that is given to a manifold by metrics, such as the flat Robertson-Walker metric. So in general, a metric gives to the manifold a global causal structure that can be highly non-trivial. causally connected events must be connected by a causal curve, which is either timelike or null. And that puts a restriction on a possible formulation of an initial value problem. In physics, we are accustomed to define dynamics where by specifying conditions at a given time will let us determine what will happen in the future or what has happened in the past. That is what defines a deterministic system. In the case of general relativity, the situation is complicated because the global causal structure of the manifold may not allow you to formulate such a problem. So what we actually want to do is to take a space-like surface which defines let's say, the initial time. So you have something that you consider to be your space at a given time, and there you have to put initial conditions that will determine what happens in the past. For example, give the initial geometry on the surface and how much is changing in its a small neighborhood around around it. So something like the derivative. Let's say you give the metric and the quote derivative of the metric, and you want to determine what will be the geometry on the manifold on any future event of that surface. But the future can be determined for future events which are causally connected only with events on S. That means if there are other events outside S that are causally connected with a specific event, then the information on S cannot fully determine what will happen there. And similarly, if you want to see what happened in the past. And you can do that only when manifolds have the property of being globally hyperbolic. So only globally hyperbolic manifolds have a well-defined initial value problem. So let's see the definitions of those terms. So let's start with any set which is a subset of the manifold. Then we can define the causal future of that set to be all the events connected to that manifold by a future causal curve, either timelike or null. And similarly, the causal past of S are the set of all the events that can be connected to S with a past causal curve. Now we can define more restrictive sets by considering events that are connected not by causal curves, timelike or null, but only timelike curves. So that defines the chronological future and the chronological past of a set S. Now, in order to set an initial value problem, we want to define conditions on sets that have the property of being achronal. So such sets are sets where no two of its points are connected by a timelike curve. So let's, for the moment, consider subsets of the manifold which are both achronal and closed in the topological sense. The future domain of dependence of the set S consists of points P such that every past moving inextensible causal curve intersects S. So that means that what happens at the point P depends solely to what was happening on the surface S. And similarly, the past domain of dependence is defined in a similar way by replacing future with past and vice versa. Now, those sets define what is called Cauchy horizons. and they are the boundaries of those sets. So you can see in this cartoon here, these are events whose past light cones intersect only points on S, and similarly here points that there are future light cones intersect only points on S, and these are the boundaries where if we go slightly outside, we will find events that are also causally connected to points outside of the surface S. So the information on S cannot fully determine what happens at points that are outside of the Cauchy horizon of that set. Therefore, if we properly define initial data on this set, that determines what happens only in the domain of dependence of the surface, which is the union of the future domain of dependence and the past domain of dependence. So everything outside here has influences by events that happen outside S. Now, if the metric and the manifold is such that the domain of dependence of a set sigma is the full manifold, then sigma is called a Cauchy surface. And the manifold is globally hyperbolic if it possesses such a Cauchy surface. Now, having a Cauchy surface in a manifold is something that many times fails to happen. The most common reason for not having a Cauchy surface is the fact that we have singularities in the metric. And as Penrose and Hawking have showed us, this is unavoidable. So, if you choose an achronal set and define initial conditions, and you use Einstein equations to evolve at future or past times, then at some finite time you will encounter some singularity, after which you cannot continue to evolve the Einstein equations. But this is not the only reason for not being able to have a globally well-defined initial value problem. Another reason not to have a Cauchy surface in a manifold is the existence of closed timelike curves. So let's consider an entertaining example which you can find in the book of Carroll, the so-called Misner space. So let's consider a space described by coordinates t and x. So this is the coordinate plane. This is the x-axis. This is the t-axis. And let's not consider the full plane, but a strip on that plane extending from x equals 0 to x equals 1, where we make the identification of the x equals 0 line with the x equals 1 line, forming a cylinder. So at given t, moving along x gives us a circle, because as we go from x equals 0, reaching x equals 1, because of the identification, we will come back to x equals 0. So it is like moving on a circle continuously here. So that means that we can also use the full plane by identifying the point x with the point x plus 1. The coordinate t ranges from minus infinity to plus infinity, and we define the quantity lambda, which is the inverse cotangent or the arctangent of t. So lambda ranges from 0 to p. Notice that this metric is defined so that it is non-degenerate. That's why we have those non-diagonal terms. The determinant of g is equal to -1. And we also notice that the coordinate vectors are not globally everywhere time-like or space-like. If we consider the norm of dt, we see that this is equal to minus cosine lambda here, and cosine lambda changes sign at lambda equal pi over 2. So this vector here is time-like for lambda less than pi over 2, and changes to being space-like at lambda equal pi over 2, and after that it is time-like between pi over 2 and pi. dx is the opposite. Its norm is equal to its norm square, is equal to cos lambda, and that changes sign from being positive for t less than 0 to being negative at t greater than 0. So you see that at t equals 0, the role of time-like vector changes from dt to dx. And that's why you see in this cartoon these cones being tilted. This null direction here coincides with the x-axis at t equals 0, and then the light cone is tilted in the almost horizontal position as we move towards later times. But you see that has the following effect. Let's consider this curve here, and you can see that at early times this is a completely space-like curve, because the tangent here is almost the vector dx, which is space-like, so that's a space-like curve. Now if you go and draw a similar curve for positive t's, you see that such a curve now is almost time-like, because now this is the time-like direction. So such a curve here is time-like, but also this point is identified with that point. So this is a closed time-like curve. So an observer moving here will come to this point and repeat her or his history indefinitely. So remember, these are events. They're not just space points that you come back at a different time. These are events at a specific x and specific t. So when the observer comes back here, she or he is the same that what she or he was, well, if you can say that, moving along this curve at early values of the parameter of the curve. But you also see that what happens on this curve is not determined by what happens on the curve sigma. So this curve here does not belong to the domain of dependence of sigma, and there is a Cauchy horizon that forms at t equals 0. So you don't want to be trapped on such a time-like curve, but well, don't worry too much. It seems that it's not a physical space-time because it's not a solution to Einstein equations with normal matter. So don't worry too much about it.